Well, first of all, I'd like to thank the organisers for inviting myself and Andy here to talk about our work on soft black hole hair. And what I'd like to do now is to describe a little bit of the work that Stephen Hawking, Andy Strominger and myself have been doing. There is one preprint on the subject and there is more to come in the very near future, we hope. So let's go back and see if we can there we go. Remember a few of the lessons that we learned from Andy's talk. The first is that there are an infinite number of charges which you can define at null infinity. At the past endpoint of future null infinity, you can define a charge for any electromagnetic field configuration, F, simply by integrating it against any spherical harmonic you like. So in this formula, you integrate over the two-sphere at the past endpoint of future null infinity, the dual of the electromagnetic field, weighted by any spherical harmonic epsilon. That gives you a charge which you can define at the past endpoint of future null infinity, Q epsilon plus. Similarly, at the future endpoint of past null infinity, you can define a charge Q epsilon minus. And the real important features of the conservation laws are that Q epsilon plus is equal to Q epsilon minus. The real problem that you have in proving statements like this is that space-like infinity is a singular point in the compactification of Minkowski space. So there is a non-trivial issue of showing that the fields are antipodally identified as you go around space-like infinity to get from I plus minus to I minus plus. So there is an issue there. It was proved by Christodoulou and Kleinemann that under a wide variety of circumstances that you can rigorously show that those are, that the fields do obey those antipodal identification laws, and that's what gives rise to these infinite number of conservation laws. One way of thinking about the conservation laws is to say that charge is preserved at every angle. Epsilon can really be any spherical harmonic, so what you're doing is showing that for each angular momentum mode there is going to be a conservation law. The way in which one can start to extend this to black holes is to think about how you actually generate this in a Cauchy problem. So you can take the charge at the endpoint, past endpoint of future null infinity and turn it into an integral over all of null infinity in the following way, simply by acting using Gauss's theorem to evaluate what this charge is. So all you need to do is to take the integral of epsilon star f, take its exterior derivative, and then integrate it over all of future null infinity. If you do that, you will turn Q plus epsilon into an integral over all of Scri. You'll have d epsilon star f plus epsilon star j. And the way in which you should interpret this is the first term here, d epsilon star f, you want to interpret as the flux of soft photons through Scri plus. So this term here is really telling you about the way in which photons emerge from the space-time out through null infinity. Epsilon star j is just the term that you would expect because there is going to be an escape of electric current through null infinity, and so that term is kind of obvious. It's just simply telling you about the charges that have left through null infinity. So this term here is soft photons, and this term here corresponds to the usual kinds of currents. The important point to get is that the effect of soft photons is to augment the usual currents. And if you think about doing scattering calculations, it's this term here which makes the conservation laws apply at all angles. The second thing which you have to recall from the flat space calculations are that the vacuum state is not a unique thing. There are many vacuum states simply because Q epsilon plus acting on the vacuum is different to the vacuum itself, the original vacuum. The fact that there are large gauge transformations, meaning gauge transformations which do not go to zero at infinity, is what gives rise to the degeneracy of the vacuum, and those are associated with the soft photons which go through infinity. So what the effect of this term is would be to change the nature of the vacuum state. Because any particular solution that you look at breaks this symmetry, you can attribute the symmetry breaking you can associate the symmetry breaking with a Nambu-Goldstone boson, which in this particular case is the photon. If you do the same thing for gravity, you will end up with discovering that the graviton is also a massless field. So what has this got to do with black holes? We have a situation that looks like this. Here we have a black hole space-time. We have up here, we've got some surface that is past null infinity. At this point here, the future endpoint of past null infinity, you can define a charge, Q epsilon minus. Up here, you've got Scri plus, and at its past endpoint, you can define a charge, Q epsilon plus. The charges at this point and this point have got to be the same. And whatever you do, you can define the total charge as being an integral over all of Scri minus over this surface and this surface, because this forms a Cauchy surface in a space-time of this form. You know that the charge is conserved, so the integral over here gives rise to a charge at this point, and that's got to be the same as the charge at this point. Here we have a black hole space-time. It's formed by a collapsing shell. So you have some object which is going in, forming an event horizon, which is the blue line here. And now you want to ask yourself, how do you manage to form the charges at the past endpoint of future null infinity? Well, of course, there's another Cauchy surface in the future, which you can describe as being a surface which looks something like that. So you can construct the charge at this point by integrating over a surface which is the union of Scri plus and this blue line. The blue line, of course, represents the horizon in this particular case. This is a region that you cannot escape from. This case is an eternal black hole, so we're just looking at what happens when you have gravitational collapse without worrying about the Hawking effect. So, of course, if you come in this way, you will reach the singularity, and one hopes, of course, that the singularity doesn't bother you in the end. So the first point is, what is to stop us constructing the charge as an integral over this particular surface? Well, the answer is nothing. You just simply apply the same formula. You can define a charge Q epsilon h, which is the integral at the future endpoint of the horizon, which represents a horizon charge, epsilon star f integrated at that particular point. If we go back to this picture, that point is going to be the future endpoint of the horizon, which is somewhere around here, or around here, depending on which side you're on. That charge you can regard as being the integral just over this blue surface here. It's equal to the soft charge on the black hole. There is nothing stopping you constructing those charges simply as horizon charges. If you apply the divergence theorem again to this object here, you'll get exactly the same formula as we had before. The exterior derivative acting on epsilon gives you d epsilon star f. That represents soft photons flowing through the horizon. There will be a second term where the exterior derivative hits the df. You can use Maxwell's equations and replace that by a current. So exactly the same picture holds for the horizon as holds for null infinity. So there will be a charge which you can say is due to soft photons flowing through the horizon or currents flowing through the horizon, depending whether it's first or the second term. Again, you can regard epsilon as being a large gauge transformation on the horizon. It changes the state of the black hole because you know that throwing some object into the black hole will change its charge. It changes the soft photon content of the black hole, but at least a soft photon generated on the horizon is an object that will simply sit on the horizon because the horizon is a null surface. The expectation value of QH will be 0 in general. That's because, as Andy showed a little bit earlier, Q acting on the vacuum gives you a new vacuum state which is orthogonal to the original one. The same is true for a black hole. If you act with QH on the black hole, you'll find a new black hole state which is orthogonal to the original one. So in general, that means that if you took the expectation value by taking the expectation value of QH here, since this state is orthogonal to BH, then you'll end up with 0. That tells you the expectation value of Q is equal to 0, and the only exception to that is going to be the case where epsilon is equal to 1, which corresponds to the case of classical electrical charge. That's the state where L is equal to 0 for that particular mode, and that corresponds to a perturbation of a Schwarzschild black hole in the direction of giving you a Reissner-Nordstrom black hole. Of course, that was noticed classically a long time ago, but the fact that the expectation value of Q is equal to 0 is what tells you, it basically gives you the reason that this phenomenon was not discovered earlier. If the expectation value is 0, you will not find it in a classical calculation. So there is a new conservation law which applies when you have black holes present in the space-time. It says simply that the charge as defined on null infinity plus the charge on the horizon in the future is equal to the total charge in the past. If we go back to this picture here, what it's basically saying is that if you construct the charge on this Cauchy surface in the past and compare it to the charge on Scri plus here and here, together with the horizon charge here, then it will be conserved. Or alternatively, you can say there is a charge here, a sort of holographic charge at the future endpoint of the horizon, together with the charge at this point on Scri, and that's equal to the total charge on the original Cauchy surface. So that's basically the conservation law that you have in the black hole case. You might ask, how do you manage to change the charge on a black hole that already exists? So here is a Penrose diagram of a black hole that forms and then evaporates. So the little brown lines that you have here correspond to Hawking radiation going off to infinity. We have a black hole formed here, and what we're going to do is, given the black hole, ask what happens if you throw in some matter. Typically this will be a just a shell of collapsing matter will make it null, so that it's moving along a line of constant advanced time. And so this corresponds to simply throwing something into the black hole. There are three interesting Cauchy surfaces here. There's one in the remote past on Scry minus here, and we can consider two different Cauchy surfaces in the future. There is a green one. This corresponds to the Cauchy surface in the infinite future when the black hole has evaporated. And there is a second one here, which is basically a part of the future null infinity and a little bit of the horizon there. So in this particular case of an evaporating black hole, charges can be defined either by integrals over the green surface or the yellow surface, but the black hole has been changed by throwing in some kind of matter along these red lines here. But whatever you do, because you have these conservation laws, Q minus is equal to the Q on the green line, which is the same as the Q on the yellow line. So the shock wave that you throw in corresponds to some current, JV, V being the advanced time coordinate, some spherical harmonic, a delta function for advanced time. I think those Z's should be V's. We're not interested in the L equals 0 case because that corresponds to a classical charge being thrown in, and then there's an R squared which comes from the conservation laws. Suppose initially that there are no photons, then as R goes to infinity, the relevant part of the two-form electromagnetic field is given there, and it gives rise to soft photons at infinity. So if we go back to this picture here, then it gives rise to soft photons here, and also soft photons on the horizon. So there will be photons with polarization vector dz of YLM, and on H there will be similar soft photons. And in that way you can change the state of the black hole. One point about this, which seems to give some kind of relationship to the Hawking entropy of black holes, is you might start to think, well, we have an infinite number of charges. Surely an infinite number of charges gives rise to an infinite entropy because there's lots of things that you can't measure. Well, in actual fact, you can't excite all of these modes in a physical process. There is a particular size of a particle. It's given by its Compton wavelength. That's its inverse mass. But you can't actually manage to make a particle smaller than the Planck scale. If you try to increase the mass of something that is elementary, eventually it will turn into a black hole, and that means that there will be a cutoff at the Planck scale beyond which you cannot have anything smaller. But if you go back to thinking about what that does on the horizon, it means you can't excite a mode which has oscillations on a length scale shorter than L Planck. That means you can't make an excitation having an area of less than L Planck squared, and thus the number of soft photon degrees of freedom is basically constrained by the area as measured in Planck units. That's a hint that this has something to do with black hole entropy, but is certainly not the whole story. Electromagnetism, as we have heard, is very similar to gravitation. There is a infinite dimensional symmetry, the Bondi-Metzner-Sachs group, which is an infinite dimensional abelian group, together with some extra little bit to do with rotations. So the super translations are just abelian on their own. That means you can pick any spherical harmonic, which we'll call F, and construct a diffeomorphism, which is given by this vector field here, F d by du, and then some correction terms involving d by dr, and some directional dependence on the two-sphere at infinity. So what this vector field does is essentially translate you along Scri+, for the case of having d by du here, and it's this vector field which is usually called a supertranslation. It preserves the classical structure of future null infinity. There is a charge associated with f, which is just equal to 1 over 8 pi times the integral over the two-sphere at the past endpoint of future null infinity of f times the Bondi mass aspect. The Bondi mass aspect is defined in this way on Scri+. It's simply the deviation from, well, it's basically the Newtonian potential weighted by 1 over r. In general, this object can be a function of the angles on the two-sphere, although that's rather different to what happens when you look at space-like infinity, where that does not happen. Just as is the case in electromagnetism, there is a flux formula, but it's rather more complicated, and this gives rise to BMS hair, either at Scri+ or on the horizon, by performing calculations in exactly the same way as we did for electromagnetism. They are technically more complicated, but we will be producing a paper describing that in the very near future. Of course, as Andy emphasized, this is not a solution to the information paradox. For one thing, we haven't actually considered all of the BMS group. There are also superrotations as well as supertranslations, and we do not really understand their nature. However, superrotations must be essential to understanding what the information paradox is. If you want to calculate black hole entropy, you can't really use supertranslations to do it, or the kind of charges you get in electromagnetism, because there would be a species problem. If you had 100 different gauge fields, you would have 100 times more charges to look at, and that will give you 100 times more entropy. That's not what happens. Hawking entropy is independent of the spectrum of particles that you have, and so it can't be something which has to do with ordinary gauge fields. There must be something special to gravitation, and superrotations are purely gravitational phenomena. We do not yet understand superrotations, but it is something that we will be looking at in the near future. We don't know whether we have too much hair. We don't even know whether we have enough hair. What would be convincing that this is the right way to look at the information paradox problem would be a proper entropy calculation, and that is something that we cannot do at the moment. We don't know that all of the information gets recorded. If you have global symmetries, they seem to have no part in this kind of picture. An example would be baryon number. That's a global symmetry in the standard model. But it's hard to see how global symmetries would fit into this picture. It's only in string theory that you have only local symmetries. And so, since this is a string theory conference, it's a good time to bring that particular point up. Even if you manage to get the right entropy, you have to ask yourself, how does all the information get retrieved in the Hawking radiation? Is it really all there? How does it come out of the black hole, assuming that the black hole does really completely evaporate? Another question that really needs addressing is the question of black hole complementarity. You'd like to think that an object going through the horizon experiences nothing strange, but if all of the information gets carried with the particle, but nevertheless appears on the horizon, that means you've violated the no-cloning theorem. You've got to explain how that comes about. You've got to explain the nature of the singularity, which classically would be described as the edge of space-time. It's a boundary of space-time. You've presumably got to get rid of that. If a particle goes over the edge of space-time, it is lost, and that means the information that it carries has gone with it. There must be some resolution to those problems. Finally, there's the issue of the future end point of the horizon in black hole evaporation. that too is a place where there is a singularity. It's a naked singularity, and as such causes you to have difficulty with the Cauchy problem. However, in black hole evaporation you never actually worry about conservation of energy. You just assume that that works, and it is presumably the case you should assume that it works for all the other moments as well. So here is a whole collection of problems, and I'd like to give you a little bit of reassurance that these are problems that we are still working on. What we have managed to do so far is a step towards solving the information paradox, but is certainly not the complete answer. But as you can see here, we're still hard at work. Thank you for listening.
Questions?
One small question. At the space-time level, can we visualize Hawking radiation as a consequence of vacuum degeneration?
Sorry, could you repeat the question? I couldn't quite hear you.
At the space-time level, it is possible to visualize Hawking radiation as a consequence of vacuum degeneration, in the sense that anyway, for example, you can difference a vacuum in one point of space-time and another vacuum at a different location of space-time and relate them via Bogol-Bose transformation, for example. I mean, can we imagine that anyway Hawking radiation is a manifestation of vacuum degeneration at the space-time level?
Well, I think that the way in which I think of Hawking radiation, you want to think of it as sort of pair creation close to the horizon, the radiation itself, the hard radiation that you actually see and measure easily. That doesn't directly impinge on the nature of which vacuum you are in, because that really corresponds to soft photons. So I think that the Hawking radiation you should regard as sort of the analogue of what you would see in LHC. When we were talking a little bit about Juan's question a little bit earlier, there was an infrared cutoff. Below a certain scale is things that which you find hard to measure. The DC effect of gravitational memory is the way in which you see the different vacua, and it's those things that you're going to have to look at if you want to see what the soft part of the picture actually is, which vacuum you're in. It's true that hard particles carry with them a cloud of soft particles, and so they will certainly change the nature of the vacuum state at infinity, and that's certainly true also for the Hawking particles. As they reach null infinity, they will have a cloud of soft particles with them, which will change the vacuum state. But any details beyond that, I think we do not really understand at the moment.
So, okay, Juan.
Juan.
How am I supposed to think about black holes in 2 dimensions?
I have to say that we have only really contemplated what to do in dimension 4, and also only in asymptotically flat space-time. In dimension 2, the problem ought to be very much simpler, partly because there are no degrees of freedom associated with it. So, but I have not thought further about it.
There is a finite number of charges.
Yes. What you say is correct.
Well, with that comment, I think we'll have to stop and move on, so we also will get coffee at some point. So let's thank Malcolm again.